Hello, everyone, and welcome back. Today, we're going to be talking about the two-sample t-test. This isn't a two-tailed test. This is a comparison of two samples rather than drawing an inference from a single sample. But we can use some of the exact same principles that we've already talked about from a one-sample t-test and apply those basic principles to a two-sample test. Only now, instead of comparing a sample to some standard or hypothetical value, we're now comparing two samples to one another. Now, these two samples could be from either an observational or an experimental study. If you recall, an observational study occurs when the researcher collects data from a sample of subjects but doesn't manipulate the conditions that some of those subjects experience. In contrast, in an experimental study, the researcher manipulates some of the conditions that the subjects are exposed to and then collects data on both the experimental subjects and the controls. So what are some examples of two-sample comparisons? Well, first, we might be interested in comparing whether blood pressure differs between patients that received a drug or a placebo. We might test whether carbon accumulation is greater in bogs or rich fens. We might test whether the timing of breeding differs between controls or food supplemented birds. And finally, we might compare the lake clarity between lakes with and without the presence of some invasive species. And so in a two-sample test, then, we might arrange our data like this, where we have two variables. One variable is our continuous variable corresponding to the measurement that we made, and the second variable is a nominal variable that identifies which sample each observation came from. So in this case, where we might be considering the effect of food supplementation on the breeding date of birds, here in this first column, we have our observations of breeding dates, and then in the second column, an indication of what the treatment was. Was this particular bird a control bird or a food supplemented bird? So we don't arrange our samples next to one another. Instead, we stack those observations on top of one another within a single variable that is our measurement and classify each observation based on the sample that it came from. Now, one important difference between a one sample and a two sample test is that in a one sample test, we're trying to test the hypothesis that the true population differs from some meaningful value or standard. So our null hypothesis then is that the population mean is equal to some standard, and our alternate hypothesis is that that population mean is different from that standard. But in a two-sample test, we're really trying to determine whether or not our two samples come from two distinct populations with different means, or whether they come from a single underlying population with the same mean. So we're testing the null hypothesis that the population means are equal, and the alternate hypothesis that the population means corresponding to the two samples then are different from one another. So before we get into some of the equations of how we're going to perform some of these calculations to answer these questions, I wanted to show you a really nice figure that Stephen Hurd put together that I think does a really good job of getting across our basic intuition about whether or not two samples come from a single underlying population or whether those two samples represent two distinct populations with different means. So what I mean by this is that in all three of the scenarios on the left, it's less convincing that these two populations, the one depicted in blue and the one depicted in red, are actually different from one another. Whereas in the figures on the right, we have more convincing evidence, or we're more compelled to conclude that these populations are in fact different. But the patterns on the left and the patterns on the right differ for three separate reasons. In the top row, the figures on the left have a small difference between their mean, whereas in the right, there's a large difference between these sample means. And so one of the things that can lead to increased conviction about the populations actually being different is a larger difference between the sample means. But this isn't the only thing that can provide some evidence for us that these populations are in fact different. The second row has sample means that are identical in the left-hand scenario and the right-hand scenario. But what differs between this scenario that's less convincing and this one over here that's more convincing is that the sample standard deviations are different. So here we have more uncertainty about what those population means are because our sample standard deviation is higher than it is over here. So when we have less variability then, we are more convinced about the same amount of difference between population means. In the final example then, we have the same difference between means and the same sample standard deviations, but what differs between these two scenarios is the sample size. A larger sample size gives us more confidence and makes for a more convincing argument that these populations are in fact distinct than we would feel if the sample sizes were smaller. So I hope that these different figures give you an intuitive sense that the differences between the population mean, the amount of variability we have within each sample, and the sample size all contribute to our intuition about whether these two samples come from two distinct populations or whether perhaps they come from the same underlying population. So in our two sample test then, we've got these three basic ingredients. Some measure of the difference between the means, some measure of the variability within each sample, and some measure of the sample size. And so all three of these things, all three of these pieces are going to contribute to our certainty about whether or not these populations are in fact different. So let's work through an example. Ben Dancer, a former PhD student of mine, performed an experiment to determine whether or not having more neighbors as a squirrel increased your glucocorticoid levels or stress hormone levels as a result of these increased social interactions with neighbors. So Ben performed a really clever experiment where he exposed some squirrels to playbacks of the territorial vocalizations of neighbors, tricking the squirrels into thinking they lived in a higher density environment than they actually did. In contrast to these treatment squirrels, Ben also had control squirrels. Now you might think the control squirrels might remain unmanipulated, but anytime we perform an experiment, we want to manipulate only the thing that we hypothesize is having an effect. And in this case, what was hypothesized to have an effect was the territorial calls themselves. But of course, you can't play territorial calls without setting up speakers and without making noise. And so as a sham control for the playback treatment, Ben included the same experimental setup with speakers that were playing chickadee calls, creating noise, having the same experimental apparatus, but not exposing the squirrels to this stimulus of having increased numbers of neighbors. And the response that Ben was interested in this case, was a measure of the female's circulating glucocorticoid levels, which he could measure from their feces based on the metabolites that are excreted from the squirrels and could be measured from the feces left behind after the squirrels are trapped and handled. And so this measure then of fecal glucocorticoid metabolites or fecal cortisol metabolites is what Ben used as his measure of the level of circulating glucocorticoid hormones in the squirrels. And now these are hypothetical data, but they're based on the idea of Ben's experiments. Suppose that Ben had 9 control squirrels and 9 experimental squirrels, each of which were exposed to the apparatus, but the experimental squirrels heard playbacks of other squirrels, and the control squirrels received the sham of chickadees. So in this case, we're testing the null hypothesis that these two population means are the same, that the circulating glucocorticoid levels in squirrels exposed to experimental playbacks were the same as those exposed to the sham controls. The alternative hypothesis in this case is that those two population means are different. So just like in any statistical test, we need to use our data to calculate a test statistic. And similar to our one sample t-test, our two sample t-test has a numerator that corresponds to the difference between the two sample means and a denominator that corresponds to some measure of uncertainty that's based on the standard deviation of the samples. So here we have a t-test statistic equal to the difference between the two sample means divided by the standard error of this difference. Now we calculate this standard error of the difference in a bit of an unusual way, and I'm not going to go into the details, but it's made up in part of this pooled variance, and the sample size of each of the samples factors into this as well. And so although it's not exactly equal to the standard error of each sample summed together, I hope you can see that the square root of a variance in the numerator and the sample size in the denominator has a lot of the same ingredients as our typical calculation of a standard error would normally have. Now, the one thing that's not familiar to you at this point is this measurement or term called the pooled variance. And the pooled variance is just a weighted average of the variance from the first sample and the variance from the second sample. So all we're doing here is using the degrees of freedom from the first and second sample to weight the variance from each sample based on how many observations came from the first sample and the second sample. So you can think of this pooled variance then as a weighted measure of the overall amount of variability that occurs within these two samples that we're trying to compare. Now, the last thing you need to know about is the degrees of freedom for this test. For a two-sample t-test, our degrees of freedom are equal to the sample size from the first sample plus the sample size from the second sample minus 2. So in essence, then, we're subtracting 1 from each of these sample sizes to get our degrees of freedom. So let's take a look at the actual numbers then in these hypothetical data. So in the experimental sample then of squirrels that were exposed to playbacks of conspecifics, we have a sample mean of 305.8 nanograms per gram and a sample standard deviation of 27.6, and the sample size in this sample is 9. In contrast, the corresponding sample from the control individuals exposed to the sham playbacks had a sample mean of 266.2 nanograms per gram and a sample standard deviation of 41.9. We also had 9 control squirrels in this hypothetical example. So then we can calculate the numerator of our t-test statistic calculation as the difference between these sample means, which we can calculate as 39.6. And now we need to calculate the denominator. And we can do this then based on the formula that I showed you on the previous slide and calculate that the standard error of the difference between the sample means is equal to 16.7. So we can use this standard error then to calculate our test statistic as 2.37. The difference between the two sample means was equal to 2.37 standard errors. So how can we use our calculated test statistic then to decide whether the population means are in fact different? Well, just like we've done in the past, what we want to do is to compare our calculated test statistic to a distribution of test statistics that we would get if the null hypothesis were true. And so the line that I've drawn here represents the distribution of t-test statistics with 16 degrees of freedom that we would get if the null hypothesis were in fact true. And what I've indicated by the edge of these blue areas is where our test statistic is in fact located. So we calculated our t-test statistic from our samples as being equal to 2.37. Now, if you recall, we had an alternate hypothesis that didn't indicate any a priori prediction about the direction of the effect. So we need to consider both the probability of getting a value as extreme or more extreme in the positive direction, as well as the probability of getting a similar value in the negative direction and more extreme in the negative direction. So if we take a look at this observed test statistic then, we can tell right off the bat that it's really pretty unusual relative to what we would expect if the null hypothesis were true. So 2.37 for a t-test statistic is actually pretty big, pretty unusual. And we can calculate then a corresponding p-value that is a two-tailed p-value corresponding to both of these areas summed together as 0.03. So because this value falls below our typical alpha level of 0.05, we would then reject the null hypothesis and conclude that there is a difference in fecal cortisol metabolites between squirrels experiencing playbacks of other squirrels compared to controls that experienced playbacks of chickadee calls. Now, in this case, it's important to remind you that there is a slightly subtle difference. Our samples were measured in our 9 observed squirrels in each of those scenarios to calculate sample means. But the reason we calculated those sample means was to try and draw inferences about the overall populations. And what those overall populations represent is all of the squirrels that are exposed or could have been exposed to our experimental treatment. And so it's important to remember that in statistics, our conclusions are about the populations, even though our statistical calculations come from the samples. Now, just as a reminder, I wanted to go through again what we're talking about when we are thinking about one-tailed or two-tailed statistical tests. When we have an a priori expectation that the population mean is below some standard, or that the calculated difference between two population means is going to be negative, then we only want to consider one tail of the distribution, and we're always considering the area to the left of our calculated test statistic. So if we had hypothesized that a population mean would be below some standard, and we calculated a t-test statistic of negative 1.8, then we would be interested in the area under this curve to the left of the value of negative 1.8. Now we would specify this in our R code using the PT command and specifying our test statistic. But in this case, by default, R always considers the lower tail of the distribution. And so we can simply use this command as it stands. In contrast, when we have a directional alternate hypothesis that leads to a one-tailed statistical test, where we're hypothesizing that the population mean is above some standard, or that the difference between the two population means is going to result in a positive value, then we only consider the upper end of the distribution, and we care about the area to the right of our test statistic. So let's say in this case, we calculated a t-test statistic of positive 1.8. In this case, we're interested in the area to the right of this value. So if, for example, we calculated a test statistic of -2, but we had hypothesized that the population mean would be above the standard and not below, then we would still be interested in the area to the right of this value of -0.2. Now, in this case, when we're asking R to provide us with a p-value, by default, R will give us the area to the left, not the area to the right. But you remember that the area to the right of any value plus the area to the left of that value is always going to equal 1, because the total area under a probability density function is always equal to 1. So in this case, instead of getting the area to the left and answering our question that way, we can instead let R give us the area to the left, and we subtract that value from 1 to give us the area to the right. So we're simply calculating this area, knowing that the value that R gives us from this command plus the area that we want is going to be equal to 1. Now, the final example in this cheat sheet is one where we have a two-tailed statistical test, where we didn't have any hypothesized direction in our alternate hypothesis. So to begin with, suppose that we calculated a test statistic of -1.8. In this case, we want to know the area to the left of -1.8 plus the area to the right of +1.8. So PT, the PT command with a test statistic of -1.8 will by default give us this area to the left. And because the t distribution is symmetrical, we can multiply that by 2 to get our two-tailed p-value. In contrast, if we got a test statistic with a value of +1.8, then we need to do a little bit of a trick again to get this area to the right instead of this great big area to the left. And we do that by our little trick of 1 minus pt to get the area to the right of our positive test statistic. And because it's a two-tailed test, we want to multiply this probability by 2. So instead of calculating our t-test statistic manually and extracting the p-value associated with that using the pt command in R, we can simply perform a two-sample t-test in R using the t.test command. So in this command in R, we need to specify our response measurement and our predictor measurement, or our vector or variable that defines which sample our observations corresponded to. Now this, I think, is the first time we've encountered this notation with this squiggly line called a tilde. And what this means is that our fecal cortisol metabolites, or our response variable, is predicted by or modeled by our explanatory variable, which in this case is which treatment group our observations belonged to. So in addition to this model specification, I've also indicated the name of the data frame, that our null hypothesis is that there is no difference between the two sample means, and that I've specified that the variances are going to be equal, or we're assuming that the variances are equal. And you can see then that this is the response that R provides, which calculates our t-test statistic, our degrees of freedom, and the associated p-value, as well as reporting the means in each of these groups and the 95% confidence interval around the difference between the two means. So we can use these results then to report our findings in the text of our results section. So here I've written out a couple of sentences that might provide a good example of how we might report results like this. Squirrels that were experimentally exposed to the playbacks of other squirrels had fecal cortisol metabolite levels that were significantly greater than control squirrels. The fecal cortisol metabolite levels of experimental squirrels were on average 39.6 nanograms per gram higher than control squirrels. And so here we have all of the necessary ingredients of the reporting of statistical results. In our text, we have indicated the significance and direction of the effect. We've supported our statement with the corresponding statistical results, including our test statistic, our degrees of freedom, and our p-value. In addition to indicating the significance and direction and supporting statistical results, I've also indicated some measurement of the effect size. How big was the effect in biological units beyond just the statistical results? And so this represents all of the things that we really want to include in the results sections when we're reporting the results of our statistical analyses. So whenever we do a statistical test, then we need to pay close attention to the assumptions of these tests. So in a two-sample t-test, then, our three assumptions are: first, that the observations are independent of one another; second, that the measurements are normally distributed; and in this case, we have a new assumption that the dispersion or variance within each of our groups is the same. And so we've now covered a one-sample t-test and a two-sample t-test. And although the recipes are slightly different, I hope you can see that the basic ingredients are pretty much the same. In both of our calculations of our test statistic, we had some measure of the effect size in the numerator and some measure of uncertainty in the denominator. So how big is the effect relative to our uncertainty? And so our t-test statistics then represent a ratio of our effect relative to our uncertainty. So in summary then, when we're comparing the means in two populations in either an observational or an experimental study, we use a two-sample t-test. The calculation of a t-test statistic in a two-sample t-test is different from our one-sample test, but it has a lot of the same ingredients, comparing the magnitude of the difference to our degree of uncertainty in what those values actually are. And once we've calculated our test statistic, we want to follow the same process for trying to determine whether or not we've seen an actual effect. And we do this by comparing our test statistic to the distribution of test statistics that we would get if the null hypothesis were true. And if our calculated test statistic is really unusual or unlikely, then we instead reject the null hypothesis and conclude that the alternate hypothesis must in fact be true. So this is our video of the two-sample t-test when our samples are independent of one another. In the next video, we'll talk about a slightly different test that we'll use when samples are in fact connected to one another.